So I think long horizon tasks are a bit of a false premise. You just need to do short horizon tasks well enough with a VLM on top during the subtask planning, and then once you chain them together, it becomes a long horizon task.
Are there any technologies you believe are underrated by the industry, yet possess substantial potential?
I'm starting to feel more and more that simulation is somewhat undervalued. I know it definitely has a lot of drawbacks, like there are many things you can't simulate well, but I think in terms of evaluation and the potential
and future potential auto research, its advantages mark a fundamental shift.
If low-level robot motion control is mostly solved, what is the biggest bottleneck for general humanoid robots?
For planning models, if we're talking about a score out of 100, I'd give them a 90. I think they're really good, very impressive. Mid-layer VLA might fail. The low-level whole-body motion, I feel that while it's not as perfect or as good as the high level, it's already passed. If you want to do reinforcement learning, you should first study simulation or first study world models. You have to solve the sampling problem before you can do reinforcement learning.
Hello everyone, welcome to the second episode of EAI Aha. I'm Xingyun. This time we're very honored to have Yanjiang Guo, a PhD student from Tsinghua University.
Yanjiang studied under Professor Jianyu Chen and has also collaborated with Professor Chelsea Finn at Stanford. His key works include Ctrl-World and video prediction policy.
His research spans reinforcement learning, VLA, and world models. I also want to share my first impression of Yanjiang. Back then, it was because our WeChat official account had written an analysis of his work, Ctrl-World. To get more traffic, we wrote a relatively eye-catching headline. He actually left a message on our backend, hoping we could change the headline to be more objective. That formed my first impression of Yanjiang, a very low-profile student who is extremely responsible for his academic work.
And here, I'd also like to thank Yiken Zhu of Current Robotics for the introduction and bridging the gap so we could have this opportunity to collaborate.
Now, let's invite Yanjiang to introduce himself and say hello to everyone.
Hello everyone, I'm Yanjiang, currently a fourth-year PhD student at Tsinghua University and about to start my fifth year. Last year, I was also a visiting scholar at Stanford. During my PhD, I've been working on embodied AI-related projects, so I've spent a lot of time researching this area. And today, I'm very happy to be here on the EAI Aha channel to share some of my past research, as well as some of the shifts in my thinking along my research journey and what I'm more interested in for the future, and so on.
Great. Thanks, Yanjiang. Thanks for your support. This is our second episode. And right at the start, I'm really grateful that you were willing to come for this exclusive interview and share your work. I think Yanjiang's academic achievements are very outstanding. So from an academic perspective, I'm quite curious, what is the work you are most satisfied with right now? Would you be willing to share it with us?
Yes, thanks for the question. Since I'm already almost in my fifth year of my PhD, compared to others, maybe my biggest advantage is that I'm a bit older and I've been grinding in this field of embodied AI for a relatively long time. And actually, when I first started, I was doing reinforcement learning. And then after that, I did some locomotion, then VLA, and then world models. Basically, as time went on, because this field has many new topics every year, I've also worked on many different projects. And if I had to choose the work I'm most satisfied with, I would choose video prediction policy, and the second would be Ctrl-World. Yeah, how about I share these two works first?
Sure. Looking forward to it. Yeah.
The first work I'd like to share is a project I completed in 2024. At the time, I worked on this video prediction policy project with my junior lab mate, Huyu Cheng. Oh, I can first share some of the background of doing this work. In mid-2024, there was a project called OpenVLA. Since OpenVLA was open sourced, many people actually started working on VLA projects. And before we did this video prediction policy, we also did some VLA related work. At the same time, another thing happened in 2024, which was at the beginning of 2024, a video model called Sora from OpenAI became very popular. After watching it back then, we felt, could this video model be more suitable as a backbone for policies? Then we started doing some research. And during our research, we found, oh, someone had already done work on using video models for policies. The most famous is the UniPy work done by Professor Yilun Du. He believes that the decision-making problem for robots can be decomposed into a video prediction problem plus an action extraction module. This way, we can shift the burden of generalization to the video prediction model. So when we finished reading Professor Yilun Du's work, we had a bit of an epiphany, like it made a lot of sense. So we started thinking about how to make further improvements and enhancements to it. Because when Professor Yilun did that work, there weren't really good open source video foundation models yet. Right. But when we were doing it in mid-2024, we found, hey, we actually already had some very powerful video foundation models, and at the same time to collect a lot of robot data. So at that point, we were thinking we wanted to make a video prediction policy. So we made the title of the paper very direct. We just hope to connect video prediction and robot policy together. And one of the biggest problems we had to overcome back then was video prediction. Although there was diffusion-based video prediction at the time, which was very powerful, as everyone knows, it requires dozens of denoising steps, which means its inference speed is very slow. On a robot, it would almost become like open-loop control. And that in robot decision-making seems to be unacceptable. So we were thinking back then, how do we speed up this process? Then one day we did an experiment. You can see this in the paper. We did an experiment and found that although video generation takes 30 or 50 steps, it has a characteristic. In the first few steps, it already presents the large-scale motion information completely. And in the subsequent denoising steps, it's actually more about making detailed corrections and adjustments to the previous denoising results. So we felt like, hey, maybe we don't need this subsequent fine-tuning process. We actually only need to take the large-scale motion from the first 1 or 2 steps. Then we trained a video model on robot data and found that indeed, after the first step, as shown in the figure in the paper, it could show very good large-scale motion information, even though it was somewhat imprecise. So our natural thought was to treat video generation only as a one-step encoder, rather than a denoiser. We directly treat it as a visual encoder, except that the representation encoded this way contains both current information and future information. So based on this idea, we treated the video generation model directly as a visual encoder and then trained a general policy. Doing it this way has a very natural benefit. We can perform cross-embodiment very naturally because video is a very general action representation space. So when we did this experiment, we found that in simulation, first in the Calvin benchmark, we got very good results. It was probably the first model at the time that could exceed an average task success length of 4. At the same time, we also did some experiments on real hardware with parallel grippers and dexterous hands and found that it had very good generalization. Yes. And this work, yes, it is also a very early work. The video foundation model we used back then was also relatively small, a 1.5 billion model. But it indeed brought me a lot of food for thought. I found that for robot decision-making, it can actually put the burden of high-level planning and semantic understanding on a very powerful foundation model. This way, our low-level policy only needs to do some tracking tasks, which can decompose the difficult task very well. Yes, and that's probably the first work I'm relatively satisfied with.
I want to make sure I understand. Is it that, for example, when you use a world model or a video generation model as a backbone,
the gap between embodiments actually becomes much smaller?
Yes, because for video, its unified interface is actually the RGB camera. This camera, what you capture is basically pixels from 0 to 255, just a lot of these 0 to 255 pixels. This way, how the robot moves will actually be reflected in this pixel space. Unlike VLA, if you want to do actions for cross-embodiment, you need to find some unified action interfaces. For example, some people will concatenate actions of different dimensions, and then some robots, single arm might occupy a certain segment of it, and some robots like dexterous hands will occupy another segment, or some people will unify it to, say, the camera coordinate system, and so on. There will definitely be a need for a unified action interface. But in video, I think it naturally completes this transfer of actions across embodiments through the image.
One quick follow-up question. For video prediction policy, what video generation model does it use?
I used a 1.5B model back then called Stable Video Diffusion because it was work done around 2023 to 2024. At that time, Stable Diffusion was super popular, right? It's the same company, and there's also Stable Video Diffusion.
Oh, stable.
Right.
We saw the results back then, but why didn't you use Sora?
Sora is not open source. Our video model needs to be fine-tuned on robot data because zero-shot video models actually, put it this way, what Sora returns to you is the final video after 50 or many steps of denoising. Usually when you ask Sora for a video, it will give you an answer in a few minutes. So this latency is something we can't tolerate. Secondly, it hasn't been specifically optimized for the manipulation domain. It's a general model, so its zero-shot performance won't necessarily be particularly good, right?
Okay. Do we have 论文 questions about this paper? Let's see if Yanjiang also has another paper Ctrl-World to share.
Okay. Before this work, I had actually just finished the video prediction policy work, and then I went to Stanford as a visiting scholar. Right, and then in video prediction policy, we actually use the video model as a policy. It will first predict the future or predict a blurry future, and then we extract the factual user actions we want from the blurry future using some modules. And back then, my collaborator Lucy was also quite interested in world models, so I wanted to continue doing some world model related work. And back then in the robotics field, actually, even today, it's a pain point. How to do evaluation is very difficult. Because anyone who has worked with real robots knows that for evaluation, if you have to roll out on a real robot, first of all, your number of rollouts is very small, which makes your distribution very narrow. The second point is that it can really consume your time and energy because you need to sit next to the robot and watch it roll out, which takes up your physical time. So in this work, we thought, since video generation is so realistic, can we build a real world, a neural world, and we'll call it a world model. Yes, that's the term. We evaluate our policy inside this world model. That was our original intention. Yes. Then we found to do this evaluation, we noticed that many previous video models had some issues. First, they were incompatible with the policy because video generation is conditioned on text, and text is a very high-level thing. So the first thing we had to do, as shown in this diagram, was to adapt this world model to be compatible with the policy. The policy's output needs to be the world model's input, and the world model's output is what the policy needs. This way, we can keep the loop going along the policy to roll out step by step inside the world model. Then we chose the best policy at the time, which was the physical intelligence Pi 0.5 policy. Then we observed its inputs and outputs, and we made some adjustments to our video generation model so that it could fully interface with this policy. Right, and the specific adjustments can be seen in the diagram below. Yes, basically, we first need to support multi-view input, and at the same time, we need to support action conditioning. Once we have these two things, we need to accurately predict how it will develop in the next step. Then we found that predicting this is actually not a very simple task because robots often have very dexterous interactions and so on, which are actually very, very hard to express visually. Then we found a particularly critical perspective, which is the wrist camera, because only from this perspective can you clearly see how it interacts. So we were thinking about how to accurately predict this wrist camera. Later, we found that we needed to add history and perform this frame level action conditioning. With these two, we can better predict the wrist camera. And by predicting multiple views, it can allow information from different views to complement each other so that it can predict, only then can it predict the next frame well. Right. And after we trained this model, we wanted to test it with the policy. After interfacing them, we wanted to evaluate it. But during evaluation, we found that it's still very difficult to accurately measure a success rate. No matter how hard we tried, we found that the world model is still hard to use for accurately measuring the policy's success rate, but we can roughly see the policy's intent in terms of instruction following. Right, because we chose the Droid platform at the time. The characteristic of this data set is that it's very diverse, and even compared to many of today's very open source data sets, it's still a very diverse data set. But its characteristic is that for some fine-grained tasks, the number of trajectories might not be very large. So we found that after learning this world model, a lot of times it gets the general idea. For example, it knows what to grab and where to put it. The general idea is there, but when grabbing, the object might deform a bit. And for example, when folding a towel, the shape of the towel after folding might have some flaws, but it roughly reflects the robot's intent. Right, so the point we claimed at the time was that we hope to use this world model to test the success rate of the policy at the instruction following level. But we felt that using it to measure an accurate success rate is not quite enough. So in our subsequent policy improvement phase, we actually also enhanced some of the policy's capabilities at the instruction following level. Right. Right, and for this work, although it has many limitations, as I just mentioned, in my view, it's also a relatively pioneering work. It trained a relatively good world model for the first time, which could interface with the state-of-the-art policy at the time and could perform actual rollouts of 20 or 30 steps. I think that was quite a meaningful piece of work at the time.
Thanks. One quick follow-up question. I'm quite curious how you handle the three-view perspective problem. For instance, do you run into issues like misalignment during generation?
The three views, this is actually a long-standing major headache, which is the issue of multi-view consistency. Our approach at the time was actually very brute force. We just concatenated the tokens of the three images together. We didn't care that much and just left it to the model to decide whether the output is consistent or not. It's a very end-to-end approach, right? We couldn't guarantee it would be consistent either. We just hoped that after learning from enough data, it would always generate consistent things. Right, that's basically the brute force solution, yes.
Since your paper has been out for some time now, given the current state of the field, are there any emerging academic solutions for maintaining consistency across the three views?
Right, I think for the work along the line of video models, they actually, basically everyone relies on more data to overcome this problem. Of course, if there are, say, some 3D reconstruction methods, they might be better for multi-view because they explicitly construct the 3D mesh. This 3D mesh provides some priors, and then you can project back to the camera you need based on the same 3D mesh. This way, your consistency can be guaranteed, right? Right. But the drawback is that 3D data is far scarcer than video, and for your multi-view cameras, you find that point clouds are very hard to align. So it also has its own set of problems. Right.
Got it. You mentioned earlier that language following performs reasonably well, but achieving finer-grained results is quite challenging. If you were to spend time revising this paper, what work would you prioritize?
Right, after this paper, actually, before I returned to China, I still had some time at Stanford, and I did a follow-up work. I spent my remaining time working on BLA. In this work, the idea was, since I can't guarantee it's very precise on many tasks, I'll select a few tasks, and on these tasks, use policy rollout data to post-train the world model. This way, I can make the world model very accurate within a relatively narrow distribution that is on certain tasks and on the distribution of policy rollouts, it's relatively accurate. And once it's accurate within this narrow distribution,
Within this distribution, at least on these several tasks, my follow-up work aims to enable policy generation that closely aligns with real-world condition. Yes, that is roughly the idea.
Thanks for sharing, Yang. I have another very curious question.
Since your academic span is very broad from RL to VLA to world model,
from the current perspective, do you have any preferred academic choices and paths?
I made a PPT slide to express some of my preferences, right? I can share it. Oh, it's really early this year. Oh, it should be early this year, right? And then I listed it in there, which is, yeah, I spend most of my time on manipulation, so I won't comment on other fields as I might not be very professional, right? In the field of manipulation, the most popular ones are actually two kinds of models. One is the VOA model, and the other is this video world model, or what we call this world action model, and so on, right? And at that time, actually, I've done a lot of work on both of these, including what's drawn here. On each final leaf branch, I might have some corresponding papers, having made some attempts. So I summarize it in this page of paper, this page of slide, right? And I also made a two-way choice for each one, and then I chose the one I prefer, right? But let me declare first, this is just my personal preference. Maybe, I think every place listed here is worth doing. There must be many places worth doing, right? And my preference is also very likely to be good, right? So I'm just sharing it with everyone. You can just look at it for fun, right? And the first branch is this VOA and world model. I think both of these, I think, in my opinion, they both have a good chance. And currently, it seems that when data is scarce, the world model might be better because video has better physical priors, right? Which is very useful for robot priors. But later on, as video gets more data, which of these two will be better? I'm actually not too sure, right? I think both are very worth studying. Now we can first look at the VOA part on the left. And for the VOA part, I'll first divide into the pre-training and post-training parts. I think both parts are definitely very important, but personally, I currently prefer doing the part related to pre-training because I think there's still a lot of room for improvement in this pre-trained model. Right. And we can first look at pre-training here. And in pre-training, at the same time, I feel that how we adjust this training recipe as well as this data recipe actually has a greater impact on this training. As for the architecture, actually, I don't think there's much need to change it because everyone start from on this VOM, and you either connect, just connect an action MOT connects an action expert, or you make a purely autoaggressive one, make an action tokenizer like this. Just these two kinds. Many people will then connect some other heads and then predict some other representation and so on, or add some learnable tokens. I think they might be much of a muchness. That is, their final train results will be about the same. Right? And what has a bigger impact is actually how you train the recipe. For example, what kind of code training you do, and then which part you train first, and then what you train next, dividing into several stages for training. This impact is relatively large. And the biggest impact is your data, right? How you prepare it, how you label it, how you segment it. This should be the thing with big impact. Right? So on this branch, I'll choose this path of training recipe and data recipe. And then in post-training, for this post-training part, I prefer this data style, me in the loop, help to accelerate this search. These foreigners are the majority. I also done some related work before I did grad. If the sample size is too small, I mean, after your sample size is too small, it leads to the improvement in the intelligence of one be limited, I think. Because in 1 hour, for example, you collect dozens of trajectories at most, and if you do it for a day, you might only get a few hundred trajectories at most. I think with these few hundred, expecting these few hundred trajectories to make this task have a qualitative leap, I think is very difficult, right? It's different from the RL of language models. The RL of language models is very cheap on this GPU. Each rollout is thousands of parallel rollouts, right? Like this is also why I think human intervention is needed. When it explores to a place where it can't get back, humans should directly recover it instead of letting it slowly explore by itself in that place, because it's really too much of a waste of time, right? Yeah, roughly, that's it.
I have a quick question. First, about post-training. If we look at the long term, say robots really enter our homes one day, do you think real robot reinforcement learning could actually work in the far future?
Right. Many robots are already deployed in real-world environments, and I think offline RL would be quite useful there. Doing online RL is still pretty troublesome because you need to control many robots at the same time to do it. If you want to do reinforcement learning, you should probably study simulation or world models first. You have to solve the sampling problem before you can do reinforcement learning. I just don't think the sample size can get high enough.
Okay, and earlier you mentioned pre-training, specifically co-training. You talked about the data recipe and what kind of data to put in at different stages of co-training. Do you have any thoughts on that? Because I've heard two schools of thought. One is that egocentric data should be in the pre-training phase, then in training is mixed training, and post-training is on real robots. Others insist that you must train end-to-end right from the start. From your perspective, do you have a preferred approach?
I think training in stages is quite necessary. A pretty standard process now is in the first stage, we first get an action tokenizer to tokenize all the robots, and then train using the original autograph next token of prediction method. During this training, you can add all the data you want, all kinds of it, right? Then in the second stage, we bring the action expert back in. At this point, you start filtering out some of the lower quality data. You select, say, some robot data or egocentric data where you feel the action labels are more accurate, and use that for training. After that, in the final stage, you probably carefully select a batch of data specifically for your own robot embodiment and train on that. Yeah, I think it generally splits into these few stages. What it's trying to achieve is to get generalization from cross-embodiment and egocentric data, while also wanting the actions to be accurate when training the action model.
Okay, but in the first stage, when you wanted to get the largest scale of generalization and a general understanding, do you think real robot data needs to be added then? Or is pure simulation data enough?
If you have real robot data, just add it right in. I think it is needed, because you have to learn that discretized token first, and after training, it can actually do quite a few tasks already, though it might just like be slower on average. And because this action token is discrete, it might feel a bit jerky. But you still need to get the model to this point first, and then in the second stage, after adding the action expert, it'll be much easier to fine-tune it, right? For specific details, you can check out Pai's paper titled Knowledge Insulation. It has a pretty detailed description of this. Just to clarify, these are just my personal preferences, right? Right, video world models. Yeah, I've done quite a bit of work on this too. Let me briefly divide them into two categories. One is world model as policy, which is what people call the world action model. The second is world model as simulator, which is using the world model as a simulator. First category, actually, I feel the biggest, most important thing is how to preserve the video model. You're using it as a policy, since what you actually want is the generalization capability of this video prediction. Right, in the first category, actually, but actually, I feel that with many of today's world action models, people make a lot of architectural adjustments. And after those adjustments, if you look at the video prediction capability, it's actually very severely degraded and damaged. Basically, in the end, it gets overfitted to just a few tasks by you. So in my view, I now prefer this two-stage training. That is, in the first stage, we need to train the video prediction well. Right. Then in the second stage, you can open this up and do end-to-end training on the actions. But I think in the first stage, you have to get the video prediction right, because you want to use this video prediction to help you generalize. If your video prediction isn't even correct, it's hard for me to imagine your policy being correct, right? So that's why I'm using this two-stage training. And then many people have a unified training route. For example, training both video and action, or some people even add action condition and action output data in all kinds of formats to train together. I don't think current models have that capacity. They haven't reached that volume yet. Doing this might cause the model to compete across different tasks, and their losses will interfere with each other. Right, so I prefer two-stage training. In the first stage, I think we just need to train the video prediction well. And then however you want to add actions later for end-to-end training, that's fine. I think that's more reasonable. And the second point is whether we should use the latent representations in the video or if we should use the clear video itself. I think we should use the latent. The benefit is, first, it's faster. We don't need to reconstruct the entire video. Second, this latent video, maybe some of its intermediate representations won't introduce extra errors. Otherwise, the video you reconstruct will still have some distributional differences from the real video, which might affect your action decision making. Second, this latent video, maybe some of its intermediate representations won't introduce extra errors. Otherwise, the video you reconstruct will still have some distributional differences from the real video, which might affect your action decision making. Right, and that's the world model part.
Another quick question. You mentioned that the latent from video represents an implicit route versus a more explicit route, and you lean more towards the implicit one because it's more efficient and might contain more general information in the latent space. I'd like to understand this claim called more general information.
Is there a clear consensus in the industry right now on what exactly this more general implicit information is? Or what do you consider to be a more general representation? Oh, I think if you get the intermediate representation, you can actually do some end-to-end training with it. Whereas if you use the final fully reconstructed video, for example, when you train the inverse dynamics model, you do it based on the ground truth video, but your reconstructed video from earlier came from the model. This actually creates a mismatch in there, right? So if you want to do it that way, you might have to add something like self-forcing, meaning you have to use the video you outputted yourself to supervise it. That is also a way of thinking, but it's also quite troublesome, right? You need to run it many times during each training session to generate that reconstructed video first, and then use it as a condition to train again. So using the latent directly has the benefit that the latent can probably already represent quite a lot of things. It's just that it doesn't express them explicitly. I think in many cases it might be enough. Also with the latent, you can use the latent from every single layer of the model, right? Because for example, with MOT, you can pass the latent through at every layer and it might contain some information. Plus you can decide at any time how far you want to reconstruct and just pull out the latent from the intermediate steps, right? I think this would result in less loss, right? Whereas the final video's loss would be equivalent to having a sort of cascaded loss in there.
Okay, great.
Then let me talk about this last part, the world model as simulator. This part corresponds to the control world-like work I mentioned earlier, as well as many subsequent works. It actually has two functions because, right, this is a model, and how to use this model is something that many people in fields like model-based reinforcement learning have already tried in various ways. First, of course, your robot can practice inside it and do rollouts. So I group this under the evaluation side because you can generate a lot of these imagined trajectories. And second, since you have this model, you can actually plan a few steps ahead during online decision making, just like model predictive control did before. You can plan a few steps first, then set a value function and select the best one. Each time there are a few action candidates, and you use this model to select a better one. Right. For this, looking at the current speed of world models, I think it falls a bit short of the planner's requirements. So I think it's better to use it for evaluation. At the same time, I think evaluation is indeed a very, very bottleneck critical issue. So I think world models have an opportunity here. Or rather, they have a chance to do it, though I'm also not sure if they can do a very large-scale evaluation, right?
All right, one quick question. You mentioned reinforcement learning is non-scalable, extremely labor-intensive, and data inefficient. So could using world model as evaluator also present an opportunity here?
Right. I think a better way is after you collect a lot of online rollout data, you fit a world model based on these online rollouts. And then you do rollouts inside this world model. Of course, the performance of this world model is also bounded by the quality and quantity of your rollout trajectories. It can only emulate the states you have visited. It's just that it preserves the states you visited through this world model rather than you having to do rollouts all over again every time the policy iterates. Right. I think it serves to improve efficiency, acting as an amplifier that can scale up your real-world rollout data. It can be built out of thin air. For example, if you don't have a single real-world trajectory, then it definitely can't simulate anything at all. And once you have a certain amount, it can preserve it for you through this world model, making it convenient for you to interact with subsequent policies. I think that's roughly its function. Yeah.
I have a few follow-up questions that we haven't covered yet, so I'd like to keep going. First, branching off into VLA and world models, could you systematically walk through the respective strengths and weaknesses of these two approaches? That's my first question.
I think actually I've been training both of these models myself all along. I feel that while world models have been quite popular recently, I think they've always been on par with VLA. In many cases, both of them are determined by your training data. A phenomenon I observed before is that if there is a very small amount of data, the world model might perform better. I think the reason is that the pre-training of the video model is closer to robot decision-making. So when the data volume is very small, this world model can bring better generalization as it can transfer the video prediction capability over. But as you get more and more data, VLA can actually gain generalization too, because as long as it learns from your data, it can learn a lot. Because your data distribution gets larger and larger, it directly fits your distribution, so it can also show a lot of generalization. As for which one will be more useful in the future when there's more and more data, that's indeed very hard to judge. Because the pre-training of these two models is very different, and the modalities of knowledge they can absorb are also very different, right? Personally, I might prefer world models a bit more, but I also can't deny that to this day, the most detailed and best demos are still mostly done with VLA. It's just that I might see better zero-shot generalization capability in world models.
You brought up an interesting point earlier. The best demos today still come from VLA. I'm curious why world models haven't produced truly striking demos even after all this time.
I feel it has to do with the modeling of the model itself. Because it needs to predict, since they are all set up as video world models now, it has to predict the video, which has relatively high uncertainty. And this makes overfitting more difficult for it. But for many fine-grained tasks, we actually want it to fit the data you collected. Right. On one hand, for VLA, first of all, people generally train VLA with relatively smaller models, and the resources needed are also smaller. Actually, for many people, when resources are limited, training VLA just works better than world models.
For one thing, many open source frameworks are fairly mature now. People have been working on DAU for a long time, and after going through numerous pitfalls, existing solutions have been well optimized. By contrast, fine-tuning world models drastically ramps up compute requirements. Moreover, as fine-tuning proceeds, the video prediction generalization capability tends to degrade. The community still hasn't found a good way to preserve this generalization. Adding extra architectural components often ends up hurting it instead. For fine-grained tasks, world models also bring greater uncertainty in future prediction compared with VLA. VLA takes images and text as input and directly outputs actions following a clean end-to-end optimization pipeline. A world action model, however, needs to predict both video and actions simultaneously. Given the huge pixel space dimensionality, its outputs come with much higher uncertainty. This uncertainty becomes noise when fitting fine manipulation tasks and often requires large volumes of data to force the model to learn the target distribution. That said, world models have their strengths. They enable better transfer of video pre-trained representations. This transfer mechanism is more natural than what VLA offers. Data sources such as cross-interaction, egocentric, and multi-view data can all be leveraged quite naturally.
We can boil this down to several key reasons. First, there are no particularly mature open source frameworks available at the moment. Second, it imposes very high computational demands. Besides, in terms of generation controllability and fine-grained performance, it still cannot match VLA at this stage.
Right, I think it can be summarized like this. One has better zero-shot generalization performance, and the other might be better for post-training on fine-grained tasks.
What steps would it need to take if finer-grained generation outputs are required?
Right, I think I have this hypothesis that in one model, the way it predicts actually has a lot of uncertainty because it might have some blurriness or some randomness, but your current observation is often just your ground truth, which is exactly the same as VLA. It just has one more blurry prediction than VLA. Right. So actually, doing fine-grained tasks and post-training, a lot of times it depends on your data distribution. That is, if your data is accurate enough with enough fine-grained operations, then actually, if you force it, you can often fit it. So I've found in some recent work, for example, it says that during fine-grained operations, I make this word action model come only look at the current frame, meaning it doesn't want to be interfered with the iterations, predictions. Just direct train the VA model, then it can overfit. Then when you look at the features, I do it, for example, when doing some high-level planning and generating actions, like which object I'm going to grasp from which angle I should grasp with kind of large-scale motion. You can look at the video prediction stuff. It can give you some like high-level guidance, and to do this balance is equivalent to making up for the defects this will have more directional model. At the same time, it also leverages its advantages, which is that it can bring very good generalization, and its guidance on a large scale is still very useful.
Got it. Here's another question regarding world models. People might think that VLA is better at long horizon tasks because its language capabilities are stronger. Do you think world models have the potential to handle longer horizon tasks?
From my perspective, when VLA handles long horizon tasks, it typically first breaks them down into subtasks before executing them. Therefore, I believe long horizon tasks and regular tasks present a trade-off.
You only need to do the short horizon task well enough with a VOM on top to do the subtask planning. Then I think once they are connected, it is indeed a long horizon task. For example, we had a previous work called hierarchical, which just use these two models, one for planning and one for low-level execution. I think this is a more reasonable framework,
including Google's recent Gemini Robotics 2,
which also has a very powerful planning model on top and a VOA model in the middle. If it's under this framework, I think anyway, both the VOA and word action model actually have to do the part below that executes the low-level policy, right? Like, so for each, the block horizon planning model is the same. So I think this doesn't exist. This problem is not that serious, right?
Got it. Thanks for going into so much detail. One final quick extra question about world models, another heavily debated topic that you touched on earlier. World models are sometimes perceived to lack sufficient controllability. First, how do you understand controllability in this context? And what methodological approaches can address this issue?
The fundamental reason lies in uncontrollability. The pixel space of images is extremely high dimensional. After pre-training, the model is trained on full video datasets, which introduces substantial randomness into its outputs. Such randomness can actually be quantified.
For example, the same cat can have hundreds or thousands of variations.
We want to directly output target actions and get the desired motion path. Yet, the model tends to generate many spurious intermediate states, which further creates challenges for controllability.
I think there are many meanings. One is that you add strong conditional.
For instance, you could replace text prompts with low-level actions similar to the approach used in Ctrl-World.
Then you can force control is robotic arm to move according to your action, like moving 1 centimeter or up 2 centimeter, left 1 centimeter, etc. This kind of very fine-grained operation. I think this is one aspect of controllability. And another aspect of controllability might emphasize that this image, it might be physically more realistic and so on. For this kind of controllability, I think we need some data that is more strongly correlated with manipulation to perform reinforcement, like doing some post-training on this video model, etc., to make it achieve a better effect in terms of controllability, right?
Very detailed explanation. Thank you so much. And then back to the two paths, which you actually also mentioned just now. This perspective is actually very fresh, that its performance is closely related to your data volume. Sometimes under a certain data volume, the VLA of some model will have the upper hand. And further ahead, do you think in the future, are they A or B, or will they combine in some way? For example, you will be other data field, combo. How to understand the relationship between the two in the future, looking ahead, say 5 years.
Right, because currently I think it's more bound by data rather than being bound by the type of model structure. What limits it must be the quality of the data, how the data is cleaned, how the data is labeled, how it's segmented. This directly determines the performance of this model, rather than whether you chose VLA or what action unified model. I think they're all the same. At today's juncture, it is definitely limited by the underlying data. Right.
Let me put it this way. I don't know if you agree, right? We might see one school of thought, like Gaudi, which hopes to train a native model from scratch using robot data, robot-related, action-related data. Another path is what Google just released, Gemini, which is a hierarchical framework and attributes reasoning agent capabilities to its top-level models. So actually, you prefer Google's solution, right?
Right. This hierarchy is also different from what many people understand as hierarchy. Many people might understand hierarchy as having a planning model on top, and then below each skill has a small skill, and different skills are called. This is hierarchy. But actually, the hierarchy mentioned here is that we have a very powerful brain on top, for example, like Gemini Robotics, ER, or GPT, this level. It has very good video understanding, memory, and some agentic functions. This is what I call the upper layer. Then down to this policy execution part, it is actually still an end-to-end model. Once you input, it's still a VLA or what action model, meaning it still inputs image instructions and then outputs the final action. In this sense, it is end-to-end, except when it needs memory and training. I think they can be separated without needing to put all the burden on one model, right? Just like the Gemini Robotics 2 recently released by Google, its top layer is actually a very powerful model based on Gemini, a Gemini Robotics model. it might be the same size as Gemini, right? It might be several hundred B or over a T in size. And it just did some more targeted post-training on robots. So its spatial understanding will also be improved. Then for its middle layer, it uses a VLA model, probably an end-to-end VLA model. Then for the lower layer, no, this time they emphasize this whole body. I don't know, I think its lower layer will also have a whole body motion tracker model to let this humanoid robot maintain balance while being able to go to its desired pose.
Here's another question. We are seeing a great many impressive mobile manipulation demos emerging. For instance, Boss Ju's current robotics released a great demo, and companies like Figure released very good demo. What is your take on this sudden surge of mobile manipulation demos?
Right. I think for mobile manipulation, there are indeed some very impressive demos like Figure and the ones done by Boss Ju current robotics. Right? I think the reason they popped up is last year the lower level whole body tracker system gradually matured, which is through a large amount of human motion and then tracking this human emotion in simulation. Basically, for any given human motion, the current humanoid can also reach your specified position. Right, after this model matured, you could use this controller to collect data of humanoids completing certain tasks. And after collecting this data, you could train a VLA to control, you could use VLA to learn from this data, right? Then you could make it output, for example, which poses the end effector of your humanoid needs to reach and where some C components need to reach, like where the waist needs to reach, where the knees need to reach. And then at this point, you connect the controller below.
Got it. This topic is a bit outside your main research focus, since your work centers on foundation models for manipulation. Let's circle back to our main discussion. Following Google's relevant releases, the term agentic has become hugely popular in the field. Some argue that agentic AI will become the next major technical direction. How do you interpret this concept, and are we actually seeing tangible shifts in practice?
An agent, in my understanding of robotic agents, refers to the upper layer planning. Like it will involve memory and error recovery and what kind of skills, subtasks to call, etc. These things actually, people have been using them before. Recently, I think the reason it's hot is because agent coding has been so successful, which makes everyone feel like we should also use this for robots. But actually, there has always been similar research in robotics, probably starting around 2023, because after large models became hot back then, people already wanted to use it to do some planning, reasoning, etc., right? But I think the core bottleneck is still in this middle layer VLA model on the model. That is, after you've planned, how do you execute the small steps it planned out? I think this is the most difficult part, and also where people have already worked for 3 or 4 years, right? And the progress of this upper layer, I think, is entirely due to the development of large models. As its capability gets better and better, for example, its V1 standing gets better and better, then it will definitely help your robot more, and space standing is better, etc., etc. Right, I think currently I can score it, this planning model, I think on a scale of 100, I can give it a 90. I think it's very good, very powerful. That is, and then this middle layer VLA might not have passed, and the lower layer whole body tracker, whole body motion tracker, I think although it's not as perfect and good as the upper layer, I think it has already passed and is already in a usable state. Last year, for example, after works like Sonic were open sourced, I think it should be in a usable state, probably a 60 or 70, I think, right?
I see. You also emphasize this now. When I talk about architecture, you emphasize the data itself. Actually, architecture is not that important. It's more about how you acquire data, how you clean it, how you get such data. So my next question is related to data. Just quite curious, what would your ideal data pyramid look like in your mind, especially in the pre-training stage? How would you arrange this pyramid?
Yeah, I think the pre-training phase should be as diverse as possible, using every kind of data, because the more variety you use, the more naturally diverse it becomes. Plus, each type of data has its own pros and cons, yeah. Like, for example, internet videos. People used to think internet videos were super diverse, but actually, I've been cleaning a lot of internet video data lately, like downloading videos from YouTube. And I found that it's not actually a perfect distribution. Because back then, I did some cleaning where I kept only the videos that contain actions, human hands, and operations. In the end, I found that what I had left were either product review videos, or food bloggers cooking, or tutorials teaching you how to make things, or repair tools, fix cars, and stuff like that. Because if you think about it, what kind of videos get put on YouTube? No one puts videos of their everyday chores on YouTube. Nobody would click on them. What you put on YouTube is either stuff you want to learn and teach others, or you're introducing a product or advertising. So I found the clean data had some very obvious biases. So yeah, even with internet videos, they have their own different distribution. It's not the complete distribution of humans actually doing everyday work. Yeah. So I think we should use whatever we can from each layer of the pyramid. Right now, the data being collected is mostly UMI data and ego data, and both have their own biases. With ego data, first of all, people are actively collecting it. As long as you're actively collecting it, there's bound to be a bias. This shift in distribution will be different from humans' everyday work. For example, operators will subconsciously want to do tasks that can be recovered. They won't do something like smashing a bottle, because once it's smashed, you can't go back. Yeah, they prefer to do tasks that are easily recoverable. And they'll do simpler tasks so they can collect data more easily. Right. And with UMI, its physical form also limits the tasks it can collect. Yeah, in short, I think all data definitely has its own bias, but we need enough sources. And then through things like deduplication, we can end up with an aggregated data set. This data set can approximate the distribution of human work. I think that's the ultimate goal.
Let's talk more broadly about industry technology. We actually just covered a lot of technical details, concepts, and buzzwords like world models, VLA, and so on. Do you feel like there are any technologies that are undervalued by the industry but actually have a lot of potential?
I'm starting to feel more and more that simulation might be somewhat undervalued by everyone. Yeah, especially recently, like as agents get better and better, I think at some point next year, they might already start doing auto research. That's when the advantage of simulation will really show, because you need simulation to let them do auto research. If you always have to run experiments and evaluations in the real world, you can't close that loop. So I'm increasingly feeling that simulation has been somewhat undervalued in recent years. And although I know it definitely has a lot of drawbacks, there are plenty of downsides, like many things can't be simulated properly, yeah. But I think for evaluation and the potential for auto research in the future, the advantages it brings should represent a very fundamental shift. I don't know if once this fundamental paradigm shift happens, it will disrupt everything that came before. So personally, I feel simulation is currently somewhat undervalued.
Discussing simulators with you just now, I also feel there have been many new changes recently.
One is the path you just mentioned, world model as simulator, including Fei Li's recent acquisition of Scenics.
So in the simulator space, do you think the more mainstream simulators in the future will be traditional simulations, or will there be some technological iterations within them?
Right, because I haven't actually studied simulation that much, but I do feel there's a group of people who have been working very hard on it. I think for some rigid body tasks or grasping, like dexterous hand grasping and certain other tasks, I think traditional simulation should be able to achieve some results, yeah. And for some tasks that it really can't simulate, that's where world model as simulator might play a role. So I think it's hard for me to judge, yeah, but I think both can indeed serve as simulators and help close the loop for auto research and evaluation, yeah. So I think both are worth researching. It's the kind that combines world models and simulation. Simulation isn't simulation in the traditional sense. It adds some things like scanning very realistic meshes and so on. Feels like it will be a scalable simulation.
You mentioned earlier that you started with reinforcement learning and then met Professor Chen. I'm actually quite curious, were you already doing reinforcement learning when you joined his group, or did your direction change after meeting him?
Actually, because I started research very late during my undergrad, it wasn't until the second semester of my junior year that I emailed Professor Chen. That was, strictly speaking, my very first research experience. I hadn't done any research before. I basically just took classes and exams. Yeah, although my grades were pretty good, I really hadn't done any research at all. And at the time, I just came up with this idea of reinforcement learning and decision making on a whim and emailed Professor Chen. I remember he replied to my email very quickly, and after talking with him, I decided to do my first research stint in his group. It was a very random thing, I think. Yeah.
I see. It feels like you and Professor Chen really hit it off. At that moment, he had just returned to China, and you became one of his very early students. I think that's a very special connection. And regarding the shift in your own research path, I wanted to ask, since you've done reinforcement learning, VLA, world models, and modularity, how did this transition happen?
Oh, right. When I first started reinforcement learning, we would train things like quadrupedal and humanoid bipedal robots in Mujoko. Then one day at RSS, I saw many quadrupedal robot dogs being deployed in real-world environments. And after a while, I found that some people were actually starting to control humanoids. Yeah, so it was very natural to use reinforcement learning to solve locomotion first. Because at first, it was like doing reinforcement learning in simulation. And then after that, there was an extra step of sim to real transfer to transfer it to the humanoid. So I think this transition was very natural. And at the time, many other students in the group were also working in this direction. Yeah. And also because that year, also in that same year, GPT came out. GPT burst onto the scene, and I was instantly drawn to this amazing thing. Soon, people were using GPT for high-level planning, and Google released the RT2 paper around that time. With these epoch-making milestones, it felt like a whole new world suddenly opened up, like Pandora's box had been opened. So at that time, after reading a lot of papers, I started replicating the RT2 paper. Yeah, and then in 2023, I started working on VLA, right? Back then, there were no open source VLAs. We just followed the description in the RT2 paper, right? And found an open source model at the time. I think it was still the Llama 2 era, and started connecting it to VLA. Once that was done, yeah, and then from mid-2023 all the way to mid-2024, it took a whole year to finish our first VLA work. Yeah, and right after we did that, Sora burst onto the scene. Those 1 or 2 years felt incredibly dreamlike. Like every year there was some epoch-making thing coming out, and you'd want to apply it to your own field. Because this field indeed had problems we couldn't solve before. And with these powerful tools, we wanted to see if there were new opportunities. So we did work on world action models, world, which is video prediction policy, and so on. So I think it was all a very natural process. Yeah. The main thread has always remained the same. We want to solve the problem of general robot manipulation. It's just that along this path, we've discovered more and more powerful tools.
I have a question I'm personally very curious about. Your background is truly top tier.
Double Tsinghua degree plus being a visiting scholar at Stanford, and many academic achievements.
Behind such a stellar background, have you ever had moments of setback or feeling lost? Would you be willing to share?
Yeah, actually, growing up, I've had plenty of setbacks. For example, back in high school, when I was doing Olympiad training, sometimes I'd do poorly on exams and realize, wow, how are there so many incredibly smart, absurdly talented geniuses out there? Yeah, and I remember one time in high school, after an Olympiad exam, I felt so miserable that I cried on my bed for a long time. But then, a few months later, I told my mom, maybe I'll go back to Olympiad training and try again. And my mom said, okay, go study a bit more. Originally, because the setback was so big, I almost didn't want to do it anymore. Yeah. After going through that, I think, first, it let me know that there are many people who are much smarter than me. Second, it later made me realize that maybe I'm not that dumb either. I'm smart enough to do many things. I think carrying this mindset, no matter what difficulties I faced in college or during my PhD, I wouldn't get too sad, nor would I get too proud. I think I would just keep my own pace in doing research. Yeah. And later, I also felt that actually many personal qualities and other character traits might be more important than how smart you are, and so on. Yeah. So, yeah. So I think even though I faced many setbacks, keeping emotionally stable and slowly overcoming them is a pretty good process. And yeah, also I wanted to say that during my undergrad, like I just mentioned, I started research very late. I think that was also a rather wrong decision I made back then. That was back in high school during my sophomore year. Actually, it should be right at the start of my senior year. After I got admitted to Tsinghua through the Olympiad, I actually slacked off quite a bit. Then in my senior year of high school and freshman and sophomore years of college, I probably didn't work as hard as before. Then by my junior year, I suddenly realized, how come everyone else has published papers and I haven't even done any research yet? So at that time, I felt quite anxious. Yeah. Then in the second semester of my junior year, since I wanted to do a PhD, I first went to a study abroad agency to ask around. They said, since you have no research experience, you probably won't get into a very good school abroad. So I started looking for PhD opportunities within the university. I was in the electronic engineering department at the time, so I emailed some professors in EE whose research directions I found interesting. Some didn't reply to my emails, and some rejected me because I hadn't done any research. Yeah. So I was quite discouraged at the time. Then one day I noticed on the IIIS website that some new professors had joined. So I emailed Professor Chen. I remember he replied to my email very quickly and invited me for a chat. And that's how I started my first research journey. Yeah. And I'm also very grateful to Professor Chen for replying so quickly to a novice who had never done research before. Yeah. I think it had a huge impact on my future and on my life for many years to come. Yeah.
You have a great eye for talent. You evaluate people's strengths from diverse perspectives.
I noticed you spent 1 year as a visiting scholar at Stanford. What motivated you to go there as a visiting scholar back then? Also, what are some notable differences you observed between Stanford and research environments in China?
Right, at the time, I initially wanted to go abroad for a visit because during my undergrad, I didn't have research experience and couldn't apply to schools abroad. I also wanted to experience and see what the academic environment in the US was like, and I could also make more friends, so I started sending out a lot of emails. Yeah. And after going through some twists and turns, when Chelsea finally agreed, I felt incredibly happy because students doing robotics have actually read a lot of work by big names like Sergey, Chelsea, and so on. So when she agreed, I was super excited. And after a few months of getting my visa sorted, I went. Yeah, and after arriving there, first of all, I felt the cultural differences were indeed quite noticeable. And yeah, if I had to point out any specific feelings or differences, I think, first of all, Chelsea is a very charismatic person. She's extremely disciplined. I heard from others that she wakes up very early every day, goes for a swim, and then goes to work and assigns work. Yeah, and she also writes code herself. Even though as a professor, she has many students to manage and advise, she still personally does things like reading papers, writing code, running experiments, and so on. Yeah, at the time I felt like I was looking at a max level human with incredibly high energy, able to do so many things. Yeah, and yeah, that was the biggest impression I got. And I feel she's a role model for everyone to learn from. Yeah.
Great. Yes, and we also have a traditional segment. The previous guest is actually someone you know, Yan Ren, who has also collaborated with you on some work, and he left 3 questions. The first question is, if low-level motion control for robots is already mostly solved, what do you think is the biggest bottleneck for general-purpose humanoid robots?
Right. This, as mentioned before, robots can be divided into 3 levels. Yanren noted earlier that systems like Gemini, if the bottom layer is done, then I think the high level, the agent, the planning, the memory and reasoning parts are also relatively mature. So challenges lie in the execution in the middle, the VLA or world action model or unified model and so on. That is how to map from a relatively small task to an action. I think that's currently the biggest difficulty.
Next question. What approaches should we take to scale up data? Whether for tabletop manipulation tasks, intent-driven tasks, gripper-related work, or humanoid robots. What do you think is the better way to scale this data?
Right. I think for data, the most important thing is diversity. And once diversity is met, the more accurate, the better, of course. And right now, looking at it, maybe the best is real robot teleoperation, which is the most diverse. And in the middle is this UMI in terms of diversity. Real robot teleoperation has the best precision, the best accuracy. And then UMI, its accuracy is slightly lower, but it's much more scalable. And then to this egocentric operation, it might be the most scalable. I think for each type, we should collect data that is as diverse and accurate as possible. And at the same time, there's also some internet data you can use, but there might also be some distribution shift. Yeah, I think it's just about using as much of what's available as possible and ensuring their diversity, alignment, and accuracy. Yeah.
The third question is, what was the biggest difficulty and bottleneck you encountered during your PhD? What do you think was the most successful choice you made during your PhD, and what was the most unsuccessful choice?
Okay. The most difficult thing was I collaborated on a paper with the previous guest before, but that paper was submitted several times and kept getting rejected. It got rejected a lot. I think that was the toughest time of my PhD. It was a paper I collaborated on with the previous guest. Yeah.
Like now, whatever you two submit gets accepted. You're like our comrades who fought side by side. So it's basically like that.
Yeah, back then, maybe we were just starting to explore on our own and neither of us had much experience. We just blindly brainstorm every day. And after brainstorming, we put a paper together and submit it. In the end, anyway, it got rejected several times. Yeah, it was pretty painful back then. Good. And I remember when I first got in touch with a really large code base, it indeed felt very difficult because back then there were no code agents, and facing a code base with dozens of folders, it just felt like a huge headache back then, very dizzying to look at. Yeah.
Okay, got it.
And then that's the question above. And another thing is you probably need to ask a question for the next guest. The next guest is Bao Yu, who is Danfei's student, and you can ask him a question.
Oh, right. Because for their group, I feel they do a lot of research on egocentric, and they also drove this wave of egocentric data collection and including scaling and so on. So I want to ask them an egocentric related question. Do you think scaling this egocentric data can ultimately support the robot's policy? To what extent? And for the second question, I also want to ask, do you think using UMI to collect data versus egocentric collecting data under the same cost investment, whose scaling curve would be steeper?
Great, and thank you so much, Yanjiang, for your time today. I've learned a lot from your understanding of technology to your reflections on your academic journey. I think you've shared so much. I also wish Yanjiang all the best and hope you publish more and better papers.